Section 7.3 is sampling distributions and the central limit theorem. There's only two objectives here, but don't let that fool you. This is a difficult concept. Objective 1 is to construct a sampling distribution of a sample mean. Up until now, what we've been doing is looking at random variables like the mean or the variance or the standard deviation or proportions. And when we do that, we have a population, and we'll take a subset of the population that we call our sample. And if I wanted to know something, let's say that our population was all college students at MCC, and I took a random sample of the college students at MCC and I asked everybody, well, how tall are you? I would be wanting to estimate what the population height is based on the results that I get from this sample. Well, in that scenario, each student's height would be considered a random variable. What we do with a sampling distribution is, instead of looking at one sample from a population, I will look at a whole bunch of different samples from the population, and instead of looking at the height for each individual person in the sample, I'll look at each sample and calculate the average height. So then I have a whole bunch of different average heights, and this distribution of these average heights would be what we call our sampling distribution. In real situations, statistical studies involve sampling several individuals, then computing numerical summaries of the samples. Most often, the sample mean, x bar, is computed. If several samples are drawn from a population, they are likely to have different values for x bar, and because the value of x bar varies each time a sample is drawn, the random variable for this sampling distribution would be x bar. Right, I'm pulling a whole bunch of different samples from the population. Let's say that I'm wanting to know the average height. So for each one of these samples, I would find the average height for each sample. Now the average height for this group may be different from the average height for this group because I'm pulling different people. They'll have different numbers. But the thing that makes this work is all of these samples have to be the same size. And the size of the sampling distribution we're going to refer to as n. It can be any number that you want it to be. So from all of these different samples in the population, each one of these samples has an average value of x associated with it. That's the x bar. Then we say the sampling distribution for the sample mean of x bar has a distribution associated with it. Here's an example that we're going to look at that will help illustrate a point that I'm trying to make. This is an example of a sampling distribution. Tetrahedral dice are shaped like a pyramid with four faces. So these dice each have four numbers on them. Each face corresponds to a number between 1 and 4. Tossing a tetrahedral die is like sampling a value from the population 1, 2, 3, 4. Just like when you roll a regular die, that would have a sample space of 1, 2, 3, 4, 5, 6. But because these are tetrahedral dice, there's only 4 sides, so this would be our population. This would be the sample space for my population. We can easily find the population mean. What I did in my calculator over here was I took these 4 numbers, 1 through 4, I did the one variable statistical analysis on those 4 numbers, 1, 2, 3, and 4, and I calculated the mean for the population. Now this is a population mean, so I just used the Greek letter mu to denote the population mean. This is the population standard deviation for the tetrahedral die. I get 1.118. That's the standard deviation for this population of 4. This would be the mean and the standard deviation then for this population. If a tetrahedral die is tossed 3 times, then my sample size will be equal to 3, and the sequence of 3 numbers observed in a sample of size 3 drawn with replacement. So I have a tetrahedral die, I toss it 3 times, and I'm looking at the average of the 3 numbers that I roll. This table then displays all the possible samples of size 3 and their sample mean. So when I'm rolling 3 4-sided die, I could roll all 3 ones, and then the average value of these 3 numbers that I roll would be 1. I could roll a 1, a 1, and a 2, and if I look at the average of these 3 numbers, I get 1.33. I could roll a 1, a 1, and a 3, and if I average those numbers, I get a 1.67. This is a simulation of all the different number combinations I could roll where the first die is a 1, the second die progresses from 1, 2, 3, or 4, and then the third die progresses 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3. You see what's going on? So this table represents every possible number combination of rolls with 3 tetrahedral dice. This is the average, these numbers right here in this column here, 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 and here are the average values of the 3 numbers that turn up when I go through all of these rolls. This would be considered a sampling distribution of size 3 because I've got 3 dice, and then the average that I roll would be these numbers here. If I average all of these numbers here for the mean, guess what I get? I get 2.5, which means that the mean of the sampling distribution is equal to the mean of the population. This is the summary for the population data. If I look at the mean for all of the different samples of size 3, all the different possible samples of size 3, if I were to calculate this mean of all of these values here in these columns here where the mean is, I would end up with 2.5. But the standard deviation for all of these numbers would be 0.6455. That 0.6455 is not the same thing as standard deviation of the population. As a matter of fact, it's a smaller number, and it's a smaller number every time. And what we observe then is that the mean and standard deviation of a sampling distribution have this known relationship. First of all, the mean of the sampling distribution is denoted by mu sub x bar and equals the mean of the population. This is our mean of sample means, and that is equal to the population mean. That means that the mean would be an unbiased statistic. Anytime the sampling distribution of something is equal to the population thing, we say that that's unbiased. That statistic is unbiased. The mean is unbiased. The standard deviation, on the other hand, ends up being smaller. If I calculated the standard deviation for all of those sample means, I would get 0.6455, which is less than the population standard deviation. It's not immediately obvious how these two quantities are related, but I'm going to tell you that the standard deviation from the sampling distribution will be equal to the population standard deviation divided by the square root of n, where n represents the sample size for your sample. The standard error is what we sometimes call this sampling distribution standard deviation. And the standard error is equal to the population standard deviation divided by the square root of n. This number right here is the standard deviation from the population. This is a formula that works 100% of the time. The mean for the sampling distribution will be equal to the population mean, and the standard error, or the standard deviation for our sampling distribution, is equal to the population standard deviation divided by the square root of n, where n is the sample size. This needs to be put on your formula sheet somewhere. So in this example, we're told that among students at a certain college, the mean number of hours of television watched per week is 10.5, and the standard deviation is 3.6. A simple random sample of 16 students, so there's your size of your random sample, is chosen for a study of viewing habits. Let x bar be the mean number of hours of TV watched by the sampled students. Find the mean and the standard deviation of x bar. So we're told the mean standard deviation is equal to the population standard deviation, and what is that? It's 10.5. We're given that number right here. We're also asked to find the standard deviation of the sampling distribution, and we know based on this formula over here that I gave you that that's going to be equal to the population standard deviation divided by the square root of n. For this particular scenario, what is the population standard deviation? 3.6. And what is our sample size? And the square root of 16 is 4, and 3.6 divided by 4 is 0.9. So there's our standard error, and this is the mean of the sampling distribution. Now, if we look back at this table that I gave you earlier that gives us all possible outcomes for 3 rolls of the tetrahedral die, the sampling distribution can be determined from the table of all possible values for the mean for a sample of size 3. The probability that the sample mean is equal to 1 is 1 over 64 because there's 64 possible outcomes for rolls. The only way to get an average value of 1 is to roll 3 ones. Well, out of the 64 possible number combinations, there's only one way that that happens, so that's 1 divided by 64. That's how we get this number right here. If my average value is 1.33, because these are all of the possible means based on the number of rolls. Well, here's 1, 2, 3 means that are 1.33, so this probability is 3 out of 64. To get an average value or an average roll of 1.67, I could roll a 113, I could roll a 122, I could roll a 131, I could roll a 212, a 221, or a 311, and that's a total of 6 divided by 64. Do you see how I'm coming up with these probabilities for these average values here from this table? I've already counted these up earlier. This would be 10 out of 64, this would be 12 out of 64, 12 out of 64, 10 out of 64, 6 out of 64, 3 out of 64, and 1 out of 64. That's how we come up with these probabilities right here. And if you go to your calculator and you put in x bar in list 1 and p of x in list 2, and you do the one variable stats, where your data is in list 1 and your frequency list is list 2, you end up getting the average value of 2.5, and the standard deviation for your sample means is going to be 0.645. I'm not going to take the time to do this on my calculator, but that's how I would do that. So I summarize this table or condense it down into this for my random variable with the associated probabilities of getting each one of those rolls. And that's where these numbers came from, in case you were curious about where they came from. Comparing those numbers to the numbers that I got up here when I just put in the 4 numbers for my population, 1, 2, 3, and 4, I see that my population mean is going to be the same as the mean of the sampling distribution, and my standard deviation down here is equal to my population standard deviation divided by the square root of n. We were told that the population standard deviation was 1.118, and if I divide that by the square root of 3, I do get that number right there. Now let's look at the histograms for a sampling distribution. In the tetrahedral die example, the population is 1, 2, 3, 4. When a die is rolled, each number has the same chance of appearing. So if my sample size is equal to 1, then I end up with a uniform distribution because I have a 25% chance of rolling a 1, a 25% chance of rolling a 2, a 3, or a 4. I end up with a uniform distribution. But if I increase my sample size to n equals 3, notice how the probabilities change. The probability of rolling a 1 and a 4 is very, very low. Remember, there was only 1 out of 64 ways that I could get a 1 for my average of those 3 dice, and there was only 1 way out of 64 that I could get a 4 for rolling those 3 dice when I looked at the average. This distribution is starting to take on a normal shape, is it not? Remarkably, it's true that for any population, if the sample size is large enough, keyword here being large, the sample mean will be approximately normally distributed. For a symmetric population like the tetrahedral die population, the sample mean is approximately normally distributed, even for a sample size like n equals 3. What if we had a skewed distribution, a skewed population? If a population is skewed, a larger sample size might be necessary in order for our distribution to start looking normal. Over here, the shape of this distribution is skewed how? It's skewed right. Let's say that I have a population where the probability of getting a 0 is 60%, so this is a higher bar. The probability of getting a 1 is a quarter, so that's going to be about right there. And as x gets larger, the probability gets smaller. I end up with this distribution that is clearly skewed right. And this is what the distribution would look like if my sample size is equal to 1. But watch what happens if I look at the average value that I get when my sample size is 3. When n is equal to 3, this is still going to be skewed right, but now I'm starting to see a unimodal thing going on right here. If my sample size increases to 10 and I'm looking at the average value of those 10 whatever they are, then this is starting to kind of move over to the middle and take on a more normal appearance. And by the time I increase my sample size to 30, I can clearly see that I have a normal distribution. Now keep in mind, this is not the distribution of an individual x, it's a sampling distribution for an average when your sample size is 30. So I take the 30 things in my sample and I look at the average value of x for each one of those, and this is the sampling distribution of the means. This leads to something that's called the Central Limit Theorem, and this theorem is critical in statistics for assuming normality. So let's look at what the Central Limit Theorem says. It says let x bar be the mean of a large, at least 30 or more than 30. Let x bar be the mean of a large simple random sample from a population with a known mean and standard deviation. Then x bar has an approximately normal distribution with the mean for the sampling distribution equal to the population mean and a standard deviation for x bar equal to the population standard deviation divided by the square root of n. As long as your sample size is large and you're looking at a sampling distribution for the mean, we can assume normality of our distribution. So given some population with a known mean and standard deviation, the distribution of the sample means will be normal with the same mean as the population and a standard deviation of the population divided by the square root of n. This is what the Central Limit Theorem tells us. This happens if n is greater than 30, or if n is not greater than 30. If you know that the original population is normally distributed, you can use the Central Limit Theorem as well. If your sample size is bigger than 30 or the population is normally distributed, this will be the distribution of your sample means. So let's look at some example problems. In example 1, we're told that a sample of size 45 will be drawn from a population with a mean equal to 15 and a standard deviation of 3.5. So I know the population mean and standard deviation. Is it appropriate to use the normal distribution to find the probabilities for x bar? Yes or no? Yes, and why is that? N is greater than 30. As a matter of fact, what will be the distribution for x bar? It'll be normal, but what will the mean be? It's going to be the same as the population mean, 15. What will the standard deviation be? 3.5 divided by the square root of 45. This is what the Central Limit Theorem gives us. Example 2. A sample of size 8 will be drawn from a normal population with mean equal to -60 and a standard deviation of 5. Is it appropriate to use the normal distribution to find probabilities for x bar? Yes or no? Even though your sample is small, because the original population is normally distributed, we can use the Central Limit Theorem. This is the distribution for the original population. X bar is distributed normally. What will be the mean for x bar? -60. And what will be the standard deviation for x bar? 5 divided by the square root of 8. This is why we can use the Central Limit Theorem. This is what the Central Limit Theorem tells us that x bar's distribution is. Example 3. A sample of size 24 will be drawn from a population with mean mu equals 35 and a standard deviation of 1.2. Is it appropriate to use the normal distribution to find the probabilities for x bar? N is less than 30 and our population distribution is unknown. Remember, in order for the Central Limit Theorem to apply, one or the other has to happen. Either your sample size needs to be bigger than 30 or your population has to be normally distributed. If both of those things fail, then you cannot use the Central Limit Theorem. Let's look back at our notes where we wrote this down. If either this happens or this happens, we're good to go. This would be our distribution for x bar. Either one or the other has to happen. Otherwise, if both of them fail, we can't use the Central Limit Theorem. In Objective 2, we're now going to apply the Central Limit Theorem to compute probabilities involving sample means. Remember when we were finding probabilities in 7.2, what did we say we used on our calculator? Let me ask you this. Do you remember looking at this table? If you want the area and you know the x's, we used a normal CDF. And with the normal CDF, we needed left bound, right bound, mean, and standard deviation. If you want the x's or the data values, and you know the area, we used the inverse norm. And for the inverse norm, we used alpha, mean, standard deviation, where alpha here had to be the area to the left of the x's that we were looking for. What did I tell you to use if you were given the area to the right? 1 minus alpha. If you've forgotten that, go back to the 7.2 lecture video. Actually, it's the 7.1 lecture video and watch that again. So we will have to draw a picture here of what's going on. Let's read example 1 and use the central limit theorem to help us find a probability. Based on data from the U.S. Census, the mean age of college students in 2011 was 25 years with a standard deviation of 9.5 years. A simple random sample of 125 students is drawn. N here is equal to 125. What is the probability that the sample mean age of students is greater than 26 years? So what I want to know is, what is the probability that X bar is greater than 26 years? My sampling distribution has a sample size of 125. Because I can use the central limit theorem, that means that I'm going to have a normal distribution with a mean of what? 25. And what is my standard deviation? In order to find this, let's start by drawing a picture. I always draw a picture of a normal distribution if I'm working with a normal distribution. So here's my normal curve. What number goes in the middle here on this normal curve? 25. It's the mean for this distribution. And I want to know what's the probability that X bar is greater than 26. So 26 is going to be to the right of the mean. So I'm going to shade everything to the right. So do you see now how I'm going to find my left bound and right bound? So now I can find the probability that X bar is greater than 26 using the normal CDF, and I use the normal CDF because I know the X's and I want the area which corresponds to the probability. So I use the normal CDF. My left bound will be the leftmost part of this shaded region, and what is that? 26. I'm not asking a trick question here. Looking at the shaded region, the area that's most to the left is 26. Now this goes off to infinity, but I don't have an infinity button on my calculator, so what number can I use for infinity? 100 will work. What do I plug in for the mean? 25. And what do I plug in for the standard deviation? 9.5 divided by the square root of 125. Now we go to our calculator and we get this number on our calculator. How do I get to the normal CDF? Second bars, 2. For my left bound or my lower bound, I type in 26. For my right bound, I need to go off to infinity, so I'm going to use 100. I'm going to use 1,000 just to err on the side of caution. The mean is 25. The standard deviation is going to be 9.5 divided by the square root of 125. And then I paste that on my home screen, hit enter, and I get 0.1196. The probability of having a random sample of 125 students with an average age greater than 26 is pretty low, 0.1196. In plain English, what this means is that the probability that a random sample of 125 college students has an average age greater than 26 is 0.1196. In our last example in this section, we're told that Hereford cattle are one of the most popular breeds of cattle. Based on data from the Hereford Cattle Society, the mean weight of a 1-year-old Hereford bull is 1,135 pounds. So the average weight of a 1-year-old Hereford bull is 1,135 pounds. Now this is the population mean with a standard deviation of 97 pounds. Are we told that this population is normally distributed? We're not told that, so we can't assume it. Would it be unusual for the mean weight of 100 head of cattle to be less than 1,100 pounds? It wouldn't be that unusual for an individual bull to have a weight less than 1,100 pounds, but what about 100-year-old bulls? Not 100 years old. What about 100 yearlings? It would be unusual, but we've got to show it. The cutoff point for usual versus unusual, remember, is 0.05. If a probability is less than 0.05, then we say that something is unusual. So for our sampling distribution, since n is equal to 100, the central limit theorem applies, and we would say the sampling distribution of the average weights would be equal to a normal distribution with a mean of what? And a standard deviation of, well, 97 divided by the square root of 100 is 9.7, because the square root of 100 is 10, and 97 divided by 10 is 9.7. So this is what I'm going to use for my distribution when I find my probabilities. So we know that this is a normal distribution that I'm finding the probability for, so I need to start by drawing a normal curve. What number will go in the middle of this normal curve for my mean? 1135. We're also asked here to find the probability that average weight for 100 bulls is less than 1,100. So looking at my graph, 1100 is to the left of 1135, and I'm going to put it over here. I don't know where it goes exactly. I'm not drawing this to scale. I just need some numbers here to help me figure out what numbers I'm going to use. Less than means to the left of, so this is going to be my shaded region. To find this probability, I use what on my calculator? What function do I use on my calculator to find a probability of a normal distribution? Normal CDF. What will I use for my left bound now? No, left bound, leftmost part of this shaded region. It's going off to negative infinity. Negative 1,000 will work. That takes care of my negative infinity. The right bound then will be the rightmost number. That's 1100. What do I use for my mean? And what do I use for my standard deviation? 9.7. And now we go to our calculators. So we hit second, bars, number 2, because that's our normal CDF. My left bound is going to be negative infinity, so I'm going to use negative 1,000. My right bound will be 1100. My mean was 1135. And my standard deviation was 9.7. I paste this on my home screen and hit enter, and that gives me this number, 1.541. Can I have a probability that's bigger than 1? You can't. That means that you need to come over here and look for this that says, oh, wait a minute, this is in scientific notation. I need to multiply this number by 10 to the negative 4, which means I need to move this decimal here how many places to the left? 4 places. And then when I move that 4 places to the left, how many zeros are in front of that 1? 3 zeros in front of that 1. So that's going to give me 0.00015. Now the question was, is it unusual to have an average weight of 1,100 pounds for 100 head of cattle? Yes, it is unusual. It's unusual because the probability of 100 head of cattle having an average weight less than 1,100 pounds is less than 0.05. This is what we got for the probability of 100 head of cattle having an average weight less than 1,100 pounds. And it's unusual because that probability is less than 0.05. 0.05 is what we use for our cutoff separating usual from unusual. After this lecture, you should know how to construct a sampling distribution of a sample mean, but more importantly, you should know what that means to us. What that means is if your population has a known mean and a standard deviation, if your sample size is larger than 30, or your population is normally distributed, then the distribution of your sample means is going to be normal with the same mean as the population, but the standard deviation is going to be sigma divided by the square root of n. And we can use this distribution then to find probabilities like we did in these last two examples. And this wraps up section 7.3.